Hello everybody, my name is Timo and I would like to talk about the DeepAlign algorithm and how we can bring the notion of alignments from conformance checking to the field of process anomaly detection. Let me start with a motivation. So the question is, given a sequence of activities of a process that we don't know, is this correct? So is it conforming with the process that generated the sequence? And without any context, we probably are not able to answer the question. Although we as researchers might spot that this process that we're talking about seems to be the process of writing a scientific paper. So we start with identify problem, develop method, we experiment a bit, then we conduct a study, and then we research our related work. This seems to be a little bit late, at least to me as a researcher, right? But let's check that by looking at other evidence we can find by looking at how other researchers are doing it. So this is a list of example executions of how other people have been doing it. And we can see, for example, that all of them seem to execute the research-related work activity in the second position. And if we look a little bit closer, we can also see that develop method always seems to be followed up by evaluate, whereas develop hypothesis seems to always be followed up by conduct study. And if we look back at our case under investigation up here, we can see that conduct study and develop method are in there. So it seems to be that this is incorrect and also research-related work is too late. And what we have done so far is exactly what process anomaly detection does. It looks at all the patterns in the data and then compares it to the case under investigation to then say, okay, this is anomalous. But this, of course, isn't really that satisfying, because now that we know that it is anomalous, we might want to know, okay, why is it anomalous and what should we have done instead? So we would much more like if the algorithm could do something like this. It would say research-related work here is too late. It should be done in the front. And also conduct study should be replaced by evaluate. And this brings us to the idea of using alignments that are very popular in conformance checking. And how can we bring them to process anomaly detection that is based on neural networks or deep learning? So now if we remove these two red ones and include the two green ones, we can now change the sequence and correct it. So now it must be correct, right? However, we can see that very easily that if I add one more piece of information, like the resource that is executing the activities, that this can still be incorrect, or even though the order of activities indeed is correct now. And similarly, if I add more case attributes, for example, if we know that the topic of this paper is a theory paper, we would expect develop hypothesis and then conduct study more than we would expect develop method. And similarly, if the decision is accept, we would also expect a minor revision to take place. Otherwise, you wouldn't directly get your final decision, at least in our example process. So in order to answer the question at the top correctly, we have to take into account all of this information, the case attributes, the control flow, which is the order of the activities, and also the event attributes. So let me show you how we have done this so far using recurrent neural networks, how we have done process anomaly detection. So what you do is you create a neural network architecture that reads in events one by one. Okay, so this event here is being represented by the activity, representing the control flow, of course, and then there's two event attributes, the user and the day of the week in which they execute the activity, and you concatenate this all together and feed it into a recurrent network. Now this recurrent network reads in activity events one by one and remembers all the events it has already seen, and which with each new event it reads in, it makes a prediction what the next event should look like, including the control flow and the event attributes. So how can we train such a network? The way you do it is you take all of your example sequences that you have in your event log, and now what we can do is, first of all, we initialize this network with a 0 state. So now it knows nothing about anything. It just, okay, now it knows, okay, I have to start predicting soon. And if we now take the identify problem activity and feed it into the network as input and use the research-related work as the output, we can make it predict, given that it has read identify problem, that it should now predict research-related work. Okay, now it will keep its internal state. So now it knows about identify problem already. Now given research-related work, we want it to predict develop method. And so on. You keep on doing this until you reach the end of the sequence, and you do this many times for all of the cases in your event log until your model is very accurate at predicting the next event. Now, once we have done that, we can now use the network that has now been trained and knows about the process. Now we can ask it questions. For example, we can again feed in the identify problem. And now what it will give us is a probability distribution of what it thinks should be coming next. Right? And we can see, in this case, it's the incorrect example from earlier, that the next activity is develop method, but the network itself gives a very low probability for this actually occurring next. In this case, only about 5%. Now what you do in process anomaly detection usually is you take the information of all of these and you take the information that you know what is the next activity and you feed that all into a scoring function that gives you an anomaly score that is high if the next activity is anomalous and low if it isn't. So now if we calculate these anomaly scores for all of the activities and we align them properly, then we can transform this into kind of a heat map picture that gives us an idea as to where the anomaly occurs. So we now know, okay, this is a diverging element and these two are diverging. Yeah? This also works, by the way, on the event attribute level. So if here the reviewer identifies the problem, which really should be the author, we can also find it in the same way. Exactly the same back here with the submission. However, there's one problem with this, and that is that develop method here is being indicated to be anomalous, which it really isn't. What is anomalous is that research-related work seems to be missing between these two, right? But the network actually reads an identified problem, develop method, finds it anomalous, and then keeps going to find that conduct study is incorrect at this point. But there's a problem in this that we just know that the sequence is already diverging at this place, but we just keep on predicting. And this, of course, can throw off the predictions we make because we keep in our memory, the network keeps in its memory, the incorrect information about develop method. So it would be much better if we could replace the develop method or fix this issue once we find it. So we see develop method is anomalous, we should include or insert research-related work in this place. And this brings us to the DeepAlign idea, where we take the exact same neural network, but we make a slight adjustment to it, which will become apparent why this is important later on. But what we do is, instead of feeding this GRU an initial 0 state, what we can do is we can make use of the case attributes. So in this case, topic and decision, we feed this through a very simple feed-forward neural network to create an initial state for this network. So we can condition it onto the case attributes. So for example, if the topic is theory, now this network knows that probably it has to predict develop hypothesis rather than method. Yeah, so this can affect the predictions this network makes. I will come back to that. But first, let's recap what we actually want to achieve. What we want to achieve is, given the sequence, we want something like, okay, research-related work should be really done in the front, and then conduct study should be replaced by evaluate. So we need kind of an operation for inserting something and deleting something from the sequence while reading it. And this brings me to the inspiration to all of this, which is a paper on bidirectional beam search by Sun et al. From a couple of years ago. And what they propose is a very simple artificial task of, given an image, a neural network should create a caption for it. But there is a clue here, and that is that the caption is already partly filled out. So you have a beginning and an end of the caption, and the network must create a sequence of words that fits in the gap. Yeah, so satisfying the beginning and the end. And what they show is that a unidirectional RNN cannot really solve this task. So we can see that here, a man on a ski slope with a how to ski. So the sentence that creates breaks down at this point. It cannot really cope with a beginning and an end. So what they propose instead is you should use a bidirectional RNN, which is just two unidirectional RNNs, and use bidirectional beam search. And thereby they can create a sequence of words that actually fits both the beginning and the end of a sentence. Now there's one issue here, or actually it's two, and the first one is that they expect one gap to exist in the sequence, whereas in our case, if we talk about anomalies, there could be multiple gaps where people have missed or skipped certain activities. And also, we need to be able to remove incorrect activities. So if I execute something that is just incorrect, and then afterwards it's going back to normal, I want to be able to remove it as well. So we have to extend the idea of the bidirectional beam search to include multiple gaps and also be able to remove activities. So to understand how it works, I first want to show how you can actually calculate the probability of a sequence under the two RNN models that we have to train. So if we use the sequence and feed this into our BINet architecture from earlier, what we can do is, given A, the probability of reading A at the beginning of a sentence is 0.9 according to the network. And then keeping in memory that we know, okay, A has already occurred, the probability of B given A has already occurred is 0.72. And so on. You can do this until the very end. So the probability of E given this beginning of the sequence is 0.27. And you can do the same for the network that reads in the activities in the reverse order, so from right to left, right? So in this case, E, D, C, B, A. Under this network, the probability is 0.25. And we can simply take the mean of the two to calculate our overall probability. So let's go for a different example. So we have seen how we can calculate the probability of the overall sequence. And now let's talk about inserting. So I've changed the sequence slightly, and now it's A, B, D, E. So what we want to investigate is how does the probability change of this sequence if we were to insert a C in the middle. So what we do is similar as before. We can calculate the overall probability for the sequence under the network, which in this case is 0.01, so very low. And we can also see that after B, this probability drops significantly. And we can do the same coming from the back. Okay, so what we have done is we have done two forward passes to both of the networks. And now the idea is to keep as much of the information as we already have without having to rerun the network in order to be efficient. So what we can do is we can split this network at this place and get rid of these two, and split this network at this place, get rid of these two, so that we get the beginning AB under the forward network and the end, which is ED, under the backward network. And now in order to approximate how inserting a C would affect the overall probability, what we can do is we can simply ask both of these networks of what they think of C as a continuation of AB in this case, or C as a continuation of ED in this case. And now if we just multiply this all together, we get an approximation of the sequence A, B, C, D, E without having to rerun the network at all. So that's the first bit. This is also what Son et al. Have already proposed in their bidirectional beam search paper. Now what we want to do is we want to look at how we can actually delete something. So in this case, we have the sequence A, B, C, X, Y, D, E, and we want to remove X and Y. And this works very similarly again. What we can do is we can use A, B, C under the forward network, and then E, D under the backward network. And we simply ignore these two. So now we just have to ask the forward network what it thinks of continuing with D, which is this D here. And then also what the backward networks think of backward network thinks of continuing with C, which is this C here. And now we multiply it all together and get an approximation of removing X and Y. Again, without having to rerun the networks at all. All right, so now that we have understood this, how does it work? So you start with your case under investigation, of course, with your two trained neural networks. And now the first thing you do is you create a probability or calculate a probability for this sequence. In this case, it's 0.05, as we already know. Now what you do is you look at all the possible insertions you can make, all of them. That's why these parentheses are here. And you also calculate how the probability changes. You do the same for all of the deletions you could make. For example, you could delete research-related work, you could delete conduct study, or both of them at once. And then you bring this all into order by ranking it by the probabilities. And now to keep to be memory efficient, you keep only the top 5. Now 5 in this case is a parameter. You could set it to anything, but 5 turns out to be a very popular choice. In the beam search, the beams that are being referred to are exactly these cases here. So we are keeping 5 beams, which now means that we have changed the sequences. And now these sequences become the normal input to the next iteration of the algorithm. So now you rerun the algorithm on each single one of these, and you keep on doing so until you reach a convergence point. And when we run it on our example, the way it looks is as follows. So the first thing it does is it actually removes both of these at once, which is very efficient. You need only one step to remove both of them. then it will insert the research related work, and then it will insert the evaluate. And then, by the way, this also works on the data perspective, because the reviewer that we knew was here earlier, we can also replace with the top one prediction of the network once we find that this is actually anomalous. And we do the same in the submission here. All right, let's talk about how we evaluated this. So we created a data corpus of 252 different realistic synthetic event logs, and we added artificial anomalies, 6 different types. So you could skip something, you could insert something, you could have a rework of more activities that already occurred. There could be an early or late execution, and also there's an attribute anomaly, which simply means, okay, the reviewer, for example, submits the paper. We compare 4 different versions of DeepAlign. So one that uses no event or case attributes at all, one that uses only case attributes, one that uses only event attributes, and then one that uses all of them. We compare it to simple conformance checking algorithms. For one, because we do not expect a process model to be available when we run these algorithms, we chose to use a discovery algorithm, and we choose the ones from the PM4Pi library, the heuristics miner and the inductive miner. And then to compare it to the best case, we also do conformance checking with a perfect reference model. So one that we create from hand to actually generate the data sets. We use the same reference model for classic conformance checking. And what we find is, interestingly, that the DeepAlign approach, DeepAlign 0 in this case, that doesn't use any of the attributes, performs way better than the heuristics and the inductive miner. And this is actually a fair comparison, because both of these also don't use the case and event attributes. And then if we look to the reference model that also doesn't use these, we get to 0.91 accuracy in detecting the anomalies or correcting them, essentially. And what we find is that once we actually start adding the case or event attributes, that we can even surpass the performance of classic conformance checking on a reference model. And once we put it all together, we actually get the best-in-class result. However, of course, the reference model and the mining approaches do not really use the case and event attributes. So the comparison down here isn't really fair. And this is something we want to also look into in the future, because there do exist both conformance checking and discovery algorithms that include the data perspective. Now I've said that that we also investigated how the noise level affects the performance. So we have tried different noise levels between 10% and 90% noisy cases in your event log, which means at least one anomaly affects the case. And what we can see is that the performance of DeepAlign case and event attributes is actually very similar to the reference model approach, whereas the other approaches have problems even when we go to higher levels of noise. So one last thing I want to show is, because I talked about using the case attributes as an initial hidden state, what you can do with it. So let's say we use as a condition that we say, okay, let's say the decision of the paper was accept and the topic was engineering. Now we can start with our 2 recurrent neural nets with an empty sequence. And what they will do is they will start generating activities. So in this case, for example, identify problem, submit, and then final decision, and so on. You let it generate until it converges. And now what we see is that, given that the topic is engineering, we find the develop method and the evaluate that we would expect. Also, because the decision is accept, we find the minor revision part in the end here. Now if we change this to, for example, topic is theory, and we let it generate, we can find that actually it generates a similar sequence, but in this case, develop hypothesis is here instead of develop method. Lastly, if we change the decision to reject now, what we can see is that now the minor revision is gone if we start to the generation once again. All right, so to conclude, what we have seen is that it's actually possible to do process anomaly correction with alignments without any a priori knowledge about the process at all. You can run it on noisy event logs, which is always nice, because the event logs you receive from your systems most of the time already include the anomalies and you can't really get rid of them. We include multiple perspectives in our algorithm, so case attributes, event attributes, control flow, the time dimension is in there. For the first time, we can show that recurrent neural nets are also able to generate alignments. And we have lastly seen the nice generative capabilities of them. So there's three things that I would like to investigate further, or encourage other researchers to do so, because the initial condition you can play around with, right? You don't have to use the case attributes, you can use latent variables. But even then, I think a data-aware discovery algorithm is very, very reasonable, even based on deep learning approaches. One thing that always is interesting is efficiency when you talk about deep learning, because you actually have to train these networks. But once you have trained them, I think the efficiency problem that you encounter with classical alignment approaches can actually be addressed by this. Now there's two things we haven't talked about, and then one thing is numerical attributes. All the attributes we talked about were categorical. And then there are data-aware discovery and conformance checking approaches, none of which were implemented in the PM4Pi library, which is why we couldn't compare it. But in the future, it would be very interesting to see if we could compare the DeepAlign approach to those approaches as well. And then to close, I would encourage everybody to look at the GitHub repository, where there's all the code is there. You can reproduce the results. And there's also Jupyter notebooks that guide you through the whole process. And then it just remains to me to thank you for listening, and hope you have a very nice digital conference.